Let's continue with lesson 5.1 on exponential functions. Here they want us to determine the correct exponential function of the form f of x equals b to the x power. So we need to determine what is b. So looking at this graph, we know it's an increasing exponential function, so we know b will be something greater than 1. So here's the basic equation, f of x equals b to the x power. What we're going to do is plug in what we know for the value of x and the value of y. They gave us a point here on the graph. So x is a 1 and y, or f of x, is 10. Solving this for the letter b, which is pretty simple, we see that b is equal to 10. So that means the base in our equation for this graph would be 10. So our equation then is f of x equals the base 10 to the x power. So this represents this graph. Doing the same thing over here, we know this is going to be an exponential function that is decreasing, and so the base is going to be a number between 0 and 1. We know that already before we even start. So starting with the basic equation, we're going to solve for b. Plugging in the x value that they gave us of 2, plugging in the y value of 4/9, and solving for the letter b, we would use the square root property and get plus or minus the square root of 4/9, which is plus or minus 2/3. But if you remember when we first described the exponential function, we said that b, the base, had to always be greater than 0. So we know this answer will not be acceptable. So base for this one is going to be 2/3. We plug it into the basic equation where the b is, so f of x equals 2/3 to the x power. This here represents this graph. Now, remember, b can be any real number as long as it is greater than 0 and not equal to 1. Well, there's a number that occurs more than any other number when we deal with real problems. And so that number has been given a special letter to represent it, the letter E, and it's referred to as the natural base. Now this number that we're talking about is an irrational number, which means it's a decimal that continues on, doesn't repeat, doesn't terminate. And so this irrational number can actually be defined as the expression 1 plus 1 over n to the nth power as n approaches infinity. So as the value of n increases, as you see in this chart, we get closer and closer to the value of e, the natural base that we're talking about. You will notice that on your calculator you have an e to the x key. And if you were to click on it now and plug in a 1 for the x value, you would get this number that you see here, rounded to however many decimal places your calculator screen will allow. So when we have this as our base, this e to the x, we refer to this as the natural exponential function. And like I said, it occurs in a lot of real-world problems. So now I want to get used to using your calculator, and so let's practice finding where the exponential key is. I know many of you know where your x squared key is, but we want to be able to raise things to powers other than just 2. So many of you will have a symbol something like this, or maybe you'll have something like y to the x power. Look for that on your calculator and try this first problem. Now keep in mind, for the rest of this chapter, parentheses are going to be very valuable to us. So you put a parenthesis, 2 divided by 11, close the parenthesis, use your exponent key to the 0.7 power. They ask us to round to 6 decimal places. So we always look at one place to the right of where they ask us to round to. If that number is 5 or more, then we round the 6th place up. If it is not 5 or more, then we leave it as is and drop everything else off. So this would be our answer rounded to 6 places. Now if you would try this, e to the 3rd power, you will probably find this e key maybe above your ln key on your calculator. So you're going to do e, then the exponent key, 3, and again rounding to 6 decimal places. This is what you should end up with. Alright, so now let's practice graphing functions, exponential functions that have the natural base e. Keep in mind, e is just representing a number, like you're familiar with pi representing approximately 3.14. E is representing approximately 2.7. All right, and so since it is a base that is greater than 1, we know we're going to have an increasing exponential graph. We plug in values of x just like we did before. So if we plug in a -1 here for x, that would be e to the -1 minus 1, which is e to the -2. Using your calculator, this is what you would get. So I plot -1.135. Plug in 0 for x, so this would be e to the 0 minus 1 or e to the -1, and that's what I get on my calculator. When I plug in 1 for x, I get e to the 1 minus 1, which would be e to the 0, and remember any number to the 0 is 1. So there's where our value of 0, 1 has moved from there to over here at 1, 1. Remember how the exponential graphs usually go through 0, 1 unless they've been shifted. Well, this graph, remember, based on the previous chapter, has been shifted to the right 1 unit. So that point moved over. Notice that our horizontal asymptote did not move because we only shifted to the right. We didn't go up or down. So the horizontal asymptote is still at y equals 0, and you can identify your domain from left to right, your range from bottom to top. The y-intercept is this value right here. Remember, that's where x equals 0, which we found on our chart, and here's the approximation for that, or here's the exact value if that's what they want you to type in, 1 over e. All right, taking a look at this one, e to the x, we know again it's going to be the positive, the increasing exponential function. The -1, notice in a different location here, the -1 here after the function is going to shift it down 1 unit. And so that point of 0, 1, which we normally have, is now here at 0, 0. The horizontal asymptote, which is normally at y equals 0, has been shifted down to y equal -1. I used the same points, plugged in for x, got my values, and plotted them. The horizontal asymptote once again helps because I know this part of the graph is going to approach it but never cross it. The y-intercept, remember, is the value where x equals 0, and so we have that in our chart as 0. All right, we're going to take a look at how to solve exponential equations. We're going to go over many different techniques throughout the rest of this chapter, so be mindful of each and every different technique and when is best to use it. All right, so here we have the fact that if you have a base raised to a power equal to the same base raised to a power, then it must be that the powers are the same as well. So u must equal v. This is referred to as the method of relating bases. And so we're going to use this technique to help us solve exponential equations where the bases are the same or can at least be written to be the same. And so if you take a look at number 35, we have 2 to the x equals 16. Well, this base is a 2 and this is a 16 right now, but we can rewrite this as 2 to the 4th power. So when you see these problems, you're going to be looking to see how can I rewrite everything so that it's the same base raised to a power. So now that I have the same base, does it seem obvious to you that the only way this left and right side of this equation will equal is if the exponents equal each other? So x must equal 4. And that is what this method of relating the bases is saying. Take a look at this next example. All right, the 1 over 9 I could write as 1 over 3 squared. And remember the exponent rule that says I can rewrite this as 3 to the -2, the reciprocal rule or the negative exponent rule. Now that they have the same base of 3, I can drop the bases and set the exponents equal to each other. X minus 1 must equal -2 for this to be a true statement. So you solve for what x needs to be, which is a -1 in this case. Here's an example involving the natural base. We're using the exponent rules first to combine the right-hand side. Remember when you multiply bases, the rule said add the exponents. Now that I have the same base on both sides of e, I drop the base and set the exponents equal to each other. I recognize it as a quadratic equation because of the x squared, and so I move everything over to one side and solve and come up with 2 values of x that will satisfy the original equation. Now you're going to encounter some different word problems involving exponential functions because, like I said, they occur in so many areas of real life. So if you take a moment to read this, you'll see that W is representing the weight that a person can lift after T weeks of working out, T representing the weeks. So it says, what is the maximum weight that a person can bench press initially? So in other words, at the very beginning of the program. So t would be 0. 0 weeks have gone by. So when you plug in a 0 for the t, and you're really going to want to make sure if you're plugging the entire thing into your calculator, the parentheses need to be around the entire exponent. And you could actually just use a time symbol in between here, or just type in 0 because you know that's what it's going to be. And so we end up with an answer of 130 pounds. When we plug in a 3 for the value of t, then our exponent becomes a negative 0.9, which again, your calculator is going to start off with a parenthesis and then you just have to close it at the end of the exponent. And this is what we end up with, rounded to 2 decimal places or rounded to the nearest whole number, which is what they wanted, I believe. And then finally, when t equals 7, this is what we would end up with. And so our final answer would be 235 pounds. The next two examples are going to deal with compound interest. In this example, we're looking at how much money will we have, A, after T amount of years of investing a principal, P, at a rate R, and having the money compounded with interest so many times a year, and that's what N is representing. So in this example, we want to know which investment would generate the most money for us. So in part A, they're telling us that we have $4,000 to invest. So that's our principal. 5 years, that's the time T. Compounded semi-annually, that means twice a year. So N would equal 2, and notice N is in 2 locations in our formula here. And then at 8%, which we convert to a decimal by dividing by 100, so that would be 0.08. You would then plug all of this into your calculator just as is, using the parentheses here, and then here again I would put the parentheses around the 2 and the 5 and maybe just put a time symbol in between, or just enter in 10. All right, and so if you do that, you should end up with this answer, which we round to the second decimal place because we're dealing with money, and so we end up with this is our investment. Do the same thing with the information from part B. Quarterly means 4 times a year, so notice N is 4. All right, and this investment is going on for 4 years, so that's why we have 4 there for T. When you plug this all into your calculator, and it's best not to round in between, but actually type the entire thing in as is. If you round in between on a problem, it tends to throw the final answer off by a little bit, and that's all it takes. So looking at our final answers and comparing them, it looks like investment B would yield the greatest total amount for us. In this example, if you took the formula we just looked at but solved for P, this is called the present value formula. This is like asking the question, how much do I need to invest now, presently, so that I can realize, say, $1 million by the time I retire? So we're looking at how much do I need now, principal, so that I can get a certain amount in a desired amount of time. So in this example, notice they say, find the present value. So we're looking for P, the principal that we have to invest. If we're going to be paid 4.5% interest, so remember divide by 100, so 0.045, compounded semi-annually twice a year, so we put 2 for the N there and there, and then for 12 years. Now notice that there's a negative sign up here in the exponent, so that's why we have that there. All right, and so when you type all of this into your calculator using the red parentheses, all right, you should end up with the final answer that we have here, rounding to the nearest hundredths place. This is how much you would have to invest today so that you could have $10,000 in 12 years. And so that is what this formula is representing.